Let's continue our lectures on optimal control gradation estimation course. And in last class we have started this constrained optimal control and derived some basic philosophies or basic principles about this constrained optimal control, largely inspired from Pointer's minimum principle. So, let us continue our discussion on those lines, and this particular lecture I will talk about little more on time optimal control rather actually. Anyway, the topics on constrained optimal control that we are talking about is first is little bit motivation, we have given that in the last class. Then Pointer's principle, we have derived that in the last class as well. And then this particular lecture I will talk in detail about time optimal control of linear time invariant systems. Okay, especially we will towards the end of this lecture we will take time optimal control of double integral system, which is a very standard kind of benchmark problem, and then we will try to demonstrate how do you kind of get the control for control for this double integral system in a closed form sense actually. Okay, and that too in a state feedback sense basically. Alright, so that is we will see that. Then the rest of the topics will contain a little bit on fuel optimal control, possibly on energy optimal control if time permits, and then state constraint optimal control, little bit glimpse of that actually. And more on that you can read in several textbooks as well actually. Alright, to start with, let us go through just one slide about summary of Pointer's minimum principle that we discussed in the last class. So, the objective was something like this, to find an admissible time history of the control variable from T0 to Tf, okay, such that all other objectives that we have been studying about throughout the course is met, but the only condition is the control is constrained actually, okay, either in a total norm sense or component wise it is constrained between plus plus certain value and minus certain value actually. So, it is constrained between the two allowable limits actually. All other things as it is, the control history subject to this control bound should cause the system governed by this nonlinear system dynamics to follow an admissible trajectory, should also optimize certain meaningful performance index, and also force the system to satisfy appropriate boundary condition. Everything is there, but only thing is this control is now constrained actually. So, what was the outcome of the analysis last class is something like this. You can still go ahead and define Hamiltonian the regular way, and still most of the conditions are satisfied. State equation is satisfied, Costate equation is satisfied, as well as boundary condition is also satisfied. The only difference is about the optimal control equation. We can't write del h by del u equal to 0 and try to solve the control. Instead of that we have to really analyze this inequality. Hamiltonian of x u star lambda is less than equal to Hamiltonian of x u lambda. So, this inequality should give us some u star actually. Okay. So, how do you get it and things like that we will discuss in this particular lecture about LTI systems and all that. Alright, so let us go ahead and start the topic. And rest of the course largely about control constraint problems, we will be interested in LTI systems only, that is linear time invariant systems, where things are easier to see, easier to analyze and visualize also basically. And interestingly, it will also turn out that even though the system is linear, the control structure will be eventually non-linear actually. So, hold your breath towards the end of this lecture, we will see that actually. Alright, so the problem is something like this. What you are interested in is to minimize the time taken for an LTI system to go from an arbitrary initial state to the desired final state. So, we start with certain point in state space and you want to go somewhere, okay, and then let us pictorially so that we start in certain initial condition x naught and we want to go certain point xf, okay, and that should happen in minimum time actually, okay. Alright. So, what we next visualize is something like, okay, we will put put an axis system, let us say, okay, we will put a axis system, let us say like this, okay, at the desired final state. So, then it turns out that the desired system, I mean desired final point is nothing but the origin actually. So, that is 0 0. So, that is without loss of generality you can do that. So, the analysis becomes easier actually. Okay. So, essentially if you drive certain initial conditions and all possible initial conditions in the state space rather towards the origin, then that is the problem which is called as regulator problem. We are interested in regulating the state about 0 0 actually. So, essentially it becomes time optimal regulator problem. We want to drive any initial condition towards the final state which is nothing but the origin in the state space actually. Okay. Alright, because you are talking about system dynamics being linear or rather LTI, the system dynamics takes in this form x dot is Ax plus Bu, where x is an n dimensional vector and u is an m dimensional vector, and this okay, and AB are actually constant matrices. Okay, and we are constant matrices actually. Okay. So, that means this satisfies the linear structure as well as time invariant things, because A and B are constant matrices actually. Alright, the key point here is the control magnitude satisfies this this constraint, or rather actually you can think about putting it in a norm sense and all that, something like norm of u is less than equal to certain capital U and all that actually. Or more structured wise, more easier to visualize is something like this. Component wise, if I take u1, u2, u3 like that, component wise they are actually bounded between certain values, and without loss of generality again we are taking that as symmetric value sort of thing. So, that one condition we can describe actually, okay, uj is less than equal to uj sort of thing. Alright, so this u minus is the lower bound or uj minus is the lower bound of this small uj, and uj plus will be the upper bound of this this small uj basically. Okay. So, again without loss of generality we can assume that these bounds are nothing but minus 1 and plus 1, and we can do that by observing the magnitude into the B matrix actually. So, if you normalize this u component wise, and this whatever this normalizing variable we can observe that in the B matrix, and then whatever the normalized variable will contain the control components, and hence we can write the control is constrained between minus 1 vector and plus 1 vector, or rather component wise this is constrained, uj magnitude is constrained to be less than equal to 1. Alright, so the assumption here is the system is state controllable. It will turn out later that this turns out to be kind of a necessary condition for something called normal time optimal control problems. Okay, if it does not satisfy, it leads to well abnormal situation, that is something like singular control and all that actually. We will see that as we go along actually. Alright, the problem here is again to restate formally, to find an optimal control u star which satisfies this component wise constraints uj mod less than equal to 1, and which takes the system from any initial state x naught to the final state 0, that is origin, in minimum time. So, that boils down to that kind of a statement, and subject to still the system dynamics being this one actually. Okay. Alright. So, step 1 we will start the solution process. First thing first, we want to put our objective in mathematical form. Okay. So, what you are interested here is time optimization, and in other words minimum time problem. So, going back to the control structure in the very first slide, this objective function needs to be defined. Okay. So, here we can take phi equal to 0 and L equal to 1, and then we will end up with this kind of a cost function T0 to Tf is nothing but Tf minus T0. So, this is the quantity that needs to be minimized. Also remember that T0 is fixed, but Tf needs to be free here, because if Tf is also fixed there is nothing to minimize really actually, that is a constant number, Tf minus T0 also becomes a constant number. We can talk about minimizing that quantity and all that. So, by default Tf happens to be a free variable here actually. Okay. Alright, now step 2 we have to start the solution procedure, because now we have a cost function, okay, L is 1 and phi is 0, and we have a state equation x dot is Ax plus Bu, and then we are ready to write the Hamiltonian actually. Okay, so h of x lambda u is something like 1 plus 1 is L plus lambda transpose f, and f is Ax plus Bu. Okay. So, that turns out to be 1 plus if I expand this quantity and also observe that I can take this transpose. I mean I can alter the transpose, because we know that in linear algebra something like x transpose y is equal to y transpose x, provided this resulting x transpose y happens to be a scalar quantity. Okay. That means this is the multiplication of two vector happens to be a scalar. So, I can really do that in a reverse sense also. In other words, it is x1 y1 plus x2 y2 plus x3 y3 like that, and this is nothing but y1 x1 plus y2 x2 like that. So, both are similar quantity. So, that operation has been carried out here. Okay. Okay, so you can write it something like Ax transpose times lambda also, and Bu transpose times lambda also, and Bu whole transpose is nothing but U transpose V transpose. We know that actually. So, okay, it's written that way. Then the state and Costate equations we can now write something like this. Also, let me kind of put a comment here that if you see the textbook and largely I am following this material from Naidu book. Everywhere you will find stars notation, I mean x star, lambda star and things like that. I thought I will simplify that by keeping only U star notation for optimal control, and x and lambda I will not put stars actually. Okay, so, but that still means that we are talking about optimal control. In other words, optimal state trajectory and optimal Costate trajectory as well actually. Anyway, so this state and Costate equation can be derived very quickly as like this: x dot is del S by del lambda, which is nothing but the same state equation with optimal control function of course. And then lambda dot is minus del S by del x, and then h being like this, we can compute del S by del x is nothing but coming from here, lambda dot is del S by del x. So, x transpose A transpose lambda sort of thing. So, this to be okay. This quantity, okay, let me do that. This quantity is nothing but x transpose A transpose lambda, and if I take derivative of that with respect to x, I think with this only this part will remain actually. So, there is a transpose missing probably. Alright, so this is how it is actually. So, x dot is Ax plus Bu, and lambda dot is minus A transpose lambda. Alright, so the boundary condition still remains same, x of 0 is x naught and x of Tf is 0, because that is our final objective, but Tf is free, remove that actually. Now, step 4 is the critical thing. We want to see what kind of optimal control that leads to actually, and remember we have to find a control U star which is optimal in such a way that this Hamiltonian what you are seeing here with respect to U star is less than equal to any other Hamiltonian with respect to a non-optimal U really. Yeah. So, that means if I substitute this Hamiltonian expression here, okay, and try to kind of see what is going on, then what I observe here is 1 and 1 will cancel out from both sides, and this quantity also remains similar. Okay, so, same rather that will also get cancelled out. So, we will end up with some expression like this: U star transpose times Q star is less than equal to U transpose times Q star, where Q star is defined something like this. Okay. For simplicity, we just define this B transpose lambda to be Q star. So, we can write it that way. Now, we have to find a U, I mean, so what does it tell us? I mean, this inequality okay, tells us that this Q star, I mean, this U star transpose Q star is nothing but minimization of this U star Q star with this constraint in place actually. Okay. So, now the question is what kind of minimum value it can really take this U really. Okay. Now, Q star happens to be, you can think of it as something like a number basically. So, Q star is already known to us. Now, we have to select a U such that this quantity will become minimum. So, obviously, we need to see two conditions here. One case is if Q star happens to be positive, okay, then obviously this is positive. So, I can drag it down by putting a minus sign here, minus 1. Okay. So, that is the best I can do as long as Q star is positive. and if q star is negative, I can do the reverse and I can still obtain the minimum by putting u equal to plus 1 actually. So, all that it boils down is, as long as q star is positive, I simply apply minus 1, and if q star happens to be negative, then suddenly I will have to apply u star is plus 1 actually. So, this can be written something like this, final solution uj star component wise again, the signum of qj star with a negative sign. This happens to be positive, then I will apply negative, if it happens to be negative, I will apply positive actually. Okay. So, in a very compact sense, we can write uj star is negative of signum of this qj star by definition is b transpose lambda, which is nothing but bj transpose lambda. Bj happens to be the corresponding column vector actually. A small spelling mistake actually. Okay, so that is how it is. Now, signum function, I think is very clear. Those of you who don't know really, this is how it is pictorially represented. As long as some quantity is less than 0, okay, then the output is minus 1. As long as positive, output is plus 1. So, if I just attach a negative sign, this objective is met actually. Okay. All right. Now, here is a case. Now, this will result in a situation where the question is whether this happens to be either strictly greater than 0 or strictly less than 0 for all time. Okay. And it turns out that it may not be the case, and if it can actually switch sign from 0 to positive to negative and things like that. Now, if that happens, then does it switch times, switch from positive to negative side in finite number of cases, or does it happen like for a segment it remains 0 and all that actually. So, that also becomes a reality now. So what we are asking here is something like that. Okay, the normal time optimal control system, the condition happens to be like this, that during this interval something like T0 to Tf or Tf star rather, because we have to find an optimum final time also. So, within this time zone, there exists a set of times T1, T2 up to T gamma j, okay, where gamma varies with 1, 2, 3 whatever number of switches and all that, where j varies from 1 to m. That means j stands for the components of the control, and gamma varies, gamma stands for like number of crossings actually. Okay. So, ultimately it will happen to cross something like T1, T2 up to T gamma j times basically at the maximum. So, there exists a set of times, this times actually T1, T2 etc. Okay, where this qj star satisfies this condition. That means, it is 0 if and only if T is exactly equal to this gamma j quantity sort of thing actually. Okay. If and only if it contain, if and only if T equal to this discrete point, then only it is 0, otherwise not 0 actually. Okay. So, that means pictorially speaking, okay, you have this time axis, okay, and we are plotting this quantity q star j. Okay. We are all asking is, okay, if it is positive, but if it changes, it will change one time in a discrete point only basically. Okay, so this is allowed, but if I talk about something like this one and it remains 0 and then it goes positive and remains 0, comes down, and this kind of things, this finite segment it becomes 0, and those kind of things are not allowed actually. Okay, if this kind of things are not allowed, but this is okay, this is there, then that is something called normal time optimal control problem actually. Okay. Okay. Otherwise, it will be called singular optimal control. So, normal time optimal controls have little more elegant solutions and things like that. So, let's study that actually. So, this is pictorially written, given also in the book. You can see that there. As long as qj can flip over, can change signs, but it has to change time at discrete point of times only. Okay. And then as per our result says, okay, as long as q star is positive, then u star is minus 1, and q star is negative, then u star is to be plus 1. So, this is what it tells us, q star happens to be positive here. So, u star happens to be minus 1, then q j star is negative here. So, u j star is positive 1, and then again this is positive here, q j star. So, u j has to be minus 1 and things like that. Okay. So, now you can very quickly see also that this is either minus 1, then suddenly goes to plus 1, okay, then stays there and again comes to minus 1 and then stays there and instantaneously changes to plus 1, stays there like that actually. So, this is I mean intuitively and also logically it is called bang control. It actually just goes to minus 1, the maximum bound, then bangs to the plus 1, the other side, then goes there and then again bangs to the other side like that actually. It's called bang control actually. Okay. Alright. So, this normal time optimal control system, the optimal control is finally given by this expression, and essentially it is a piecewise constant function of time. I mean this is constant but for a piece, and then again it is a constant for a piece and things like that. And you can clearly see that the solution nature happens to be nonlinear actually. Okay. It doesn't stay linear, even if you plot with respect to x actually, we will see that little later, it doesn't remain linear actually. This is what is plotted with respect to time, but even if you plot it with respect to state, it doesn't remain linear really. Okay. Alright, so this is bang control actually. Okay. Alright, now if that doesn't happen, so that in other words qj not only remains positive or changes sign at finite point of time. Okay, this changes time, I mean signal at a discrete point here and discrete point here, but it also remains 0 for a finite interval of time. Okay, t1 to t2. Okay, and then that is called singularity interval, and the resulting control is called singular control sort of thing actually. Okay. In other words, the problem is called singular time optimal control, where in this segment T1 to T2 control is really not defined. Okay. And while implementing, okay, you can put it 0 and things like that because it's not defined. So, I'll continue to apply 0, but that's not the case here. The mathematically speaking, within T1 to T2, the control is really not defined. Okay. So, that is what is mentioned here. During singularity intervals, the time optimal control is not really defined. Alright, so in that case it is called singular time optimal control. It is not very elegant because of this undefined nature of the control structure and all that. Alright, now the condition is, suppose it happens like that, then very natural question is when does it happen? Okay, so we like to know that actually. Okay. So, for that we need to find a solution of lambda and all that. So, let us start doing that actually. So, now assume that lambda 0, initial condition of lambda is not, I mean that is not 0, okay, that is some value lambda naught, and then u star is the negative signum of q star, but q star is b transpose lambda, but lambda is time varying, lambda of t really, okay, but lambda dot, remember lambda dot we derived some time back here, is minus A transpose lambda. Okay. So, that is what is written here, okay, minus signum B transpose, this B transpose coming from here, and lambda is nothing but e to the power minus A transpose t times lambda naught. That's because, okay, lambda dot, okay, is A transpose lambda, okay, okay, minus A transpose lambda really. Okay. So, the solution of lambda happens to be e to the power minus A transpose t times lambda naught. From linear system theory is very clear. Alright. Now, component wise, if I try to analyze that, then all that I have to do is instead of B transpose, I will put Bj transpose really. Okay, that will lead to my Uj star actually. So, if Qj star happens to be equal to 0 throughout this interval, identically equal to 0 throughout this interval, then obviously one observation is in this interval all its derivatives are also 0. It's not only the function is 0, but because it is 0 and constant 0 throughout this interval, then all its derivative needs to be 0 as well actually. Okay. So, that means Qj star is 0, Qj star dot Now that also can be computed from this expression now with A transpose will come here. Okay, that will become 0. Well, all these negative signs will keep changing and all that actually. So that is ignored here, but I mean, if you take derivative of that, then negative sign will come here, and this will be positive again. The other one, third derivative will be negative like that actually. All right, so that doesn't matter. The question here is if negative sign is 0, then positive sign is also 0 actually. So that can be omitted also basically there. Okay. Anyway, so coming back, Qj star is 0, Qj star dot is 0, Qj star double dot is 0. You keep on doing that. And then in the process, this resulting matrices will turn out to be all 0 actually. Okay. So for better analysis, we will take positive quantity only basically. Otherwise, this can be forgotten actually. Okay. Alright, so up to q n minus 1, the 1th derivative if you take, that happens to be like that, and hence combining all the results, you can really write that okay, Gj transpose is E transpose e to the power a minus a transpose t lambda 0 is 0. Okay. Now Gj happens to be this matrix. If you see this carefully, okay, Gj happens to be Gj transpose is collection of all these transposes and all that. So Gj, okay, with transpose of everything, then it will flip. So this will become a times b. This will become a square times bj, like that actually. Alright, so all these are collected here, and they tell okay, Gj happens to be bj, abj, like that actually there. Now if you do that, repeat that exercise for j equal to 1 to m and all that, so it will turn out to be this expression. Okay, all these bj's can be combined and then analyzed appropriately, and then put it together. Then it turns out to be that G transpose e to the power minus a transpose t times lambda naught is equal to 0. Now the thing that is that can be observed is any exponential function of time is never 0. Okay. It happens to be 0 only at t equal to minus infinity, provided a transpose is positive, or plus infinity if a transpose is negative. But that doesn't, I mean, sorry, yeah, e to the power minus a transpose t never 0. That's more important actually. Okay, for all finite time intervals and all that. And by nature, lambda naught is not 0 also. Okay, we started doing that. And then the only possibility of having, I mean, this only possibility that this equation will have a solution is when this matrix is actually singular. Okay. So what you are telling here, this situation, okay, this situation arises only when this matrix becomes singular actually. Okay, and you can very clearly see that this is nothing but the controllability matrix actually. Okay. So in other words, for normal time optimal control problems, G must be non-singular. That means the system should be completely state controllable. Okay. So if the system happens to be state controllable, and then this condition, this singular optimal control condition is not satisfied, and hence we will end up with normal time optimal control problems. Okay. So let us assume that our subsequent systems are actually controllable, and then carry out further thing actually. Before doing that, some observations here. Singular intervals cannot exist for a completely controllable system, because this condition will not be satisfied actually. The second one is the necessary and sufficient condition for normal time optimal control is that the system is completely state controllable. Or conversely, you can also tell like this, the necessary and sufficient condition for the singular time optimal control is that the system is uncontrollable actually. Now there is also interesting theorems which tells us some uniqueness nature of the problem, okay, and tells that okay, when is the solution unique? The next question is that actually. So this turns out that if the time optimal system is normal, okay, then the optimal control solution is also unique. Okay, it cannot have multiple solutions and all that. And in that situation, there is also an interesting observation in the form of a theorem, which tells us that how many maximum number of switches can there be. And the theorem tells us that if the original system is normal, that means state controllable, and if all n eigenvalues are real, Okay. Then u star can switch at most n minus 1 times actually. That means all switching from minus 1 to plus 1 and from plus 1 to minus 1 counted, if you count all that, then maximum number of switches can be at the most n minus 1 actually. Okay. So, let us see that I mean these are the observations which will help us a little later also basically. Alright, the structure of the time optimal control now, about all these observations and all, we can derive certain structural form of the control solution really. So, the problem is again, just to summarize, we have a state equation something like this, linear time invariant system. Subject to this control constraint, okay, objective is x naught should be driven towards 0 with minimum time under these constraints actually. And the solution that we derived is something like this, uj star is the negative signum of Vj transpose times lambda or something like this. Okay. Lambda solution is this one actually. So, then somebody can think about a easy way of doing that okay, well, if this is the case, then the only thing that is not known to me is really lambda naught, okay, the initial condition of lambda naught. Then, well, I can start with some guess value, I will guess some lambda naught, then everything else will be self driven. Now, this expression can evolve once lambda naught is known to us actually. Okay. So, I keep computing this expression and evaluate the negative signum of that expression really actually. So, that is my uj star, that is all. So, I assume lambda naught, compute lambda of t, evaluate uj star, okay, uj star is like this, okay, and then solve for the system trajectory in parallel as well, because once uj star is known, everything is known for this system actually. Okay. Now, this becomes a kind of an explicit function of time. So, this is known to us. So, starting from any initial condition, okay, that which is known to us anyway, we start integrating the system dynamics. Okay. And then observe that for some finite time Tf, where xtf is going to 0 or not. Okay. And if Tf becomes sufficiently large, we are not happy about that, we know that it is not going to happen, then we terminate that procedure or that integration process, come back and guess a different lambda naught actually. Okay. So, we change this lambda naught and repeat the procedure. Okay. This is actually an open loop structure, where lambda naught you guess and hope for the best. If it does not happen, you change the lambda naught and again repeat the procedure, again hope for the best. Now, obviously, it is not a very good strategy, and we can end up with this infinite loop sort of thing, unless there is a mechanism where lambda naught can be adjusted in an appropriate direction or appropriate increment, so that the subsequent iteration can lead me to a better result. And remember, Tf is free variable, okay, and so it is even more difficult to find out what Tf is there and all that actually. Okay. So, this procedure, even though it is very simple, it's actually not really very useful. Okay. So, this open loop structure is not very elegant, but still somebody wants to implement it, this is the way to do that. You know this initial condition of the state. Okay. Now, you can start this iteration, okay, guess the lambda naught and go to this Costate equation, find out lambda star, and then multiplying with that and all that, you will give q star. Well, the book notation is big Q, but what you see here is small q. Okay. So, this negative q star sort of thing. Okay. So, then you can pass through a relay function and all that, you will get u star and then continue that iteration, and finally, you are assuming that okay, after some time whether xf is 0 or not. Okay. If Tf is sufficiently large and xf is still not 0, then okay, well, my guess itself was not good. So, I will change this lambda naught and repeat the procedure actually. Alright. So, again, as I told, that is not very elegant. What you are looking for is something like a closed loop structure. In other words, control should be some form of a state feedback form. And remember that in a regular LQR system, where the objective was also fairly similar, but we did not have this control constraint in place actually. Okay. Then what we had this U transpose equal to minus R inverse V transpose P times X basically. So, essentially we are having a closed form formula basically in state feedback form. So, here also we are looking for something like that, is it feasible or not. or in other words u star can be written as negative signum of this h of x, and because we also see that this is lambda, and lambda in regular LQR it was nothing but p times x. We can write it here, we know that, but still getting inspired from that we can observe that the moment somebody writes p times x here, this essentially becomes a state feedback form. Okay. So, similarly we are hunting out for an expression for h of x, okay, which will solve the similar purpose actually. Okay. Alright. So, any analytical and computational algorithm, essentially we are talking about this kind of a structure where we know that h of x is nothing but b times lambda, but what you are looking for is lambda as a function of x actually, okay, which is where x itself is time varying depending on the system dynamics and all that actually. So, essentially this function needs to be developed, okay, what you are seeing there, and that depends on problem to problem actually. So, essentially next few lectures and next few slides I will take you through some this idea of how to develop this through this standard benchmark example problem, which is nothing but a double integrator system actually. Okay. But once you have this in place, okay, this, so let us say you have this h of x in place, then the operation becomes much easier. This is you take this x star out of this and then pass it through this algorithm of whatever algorithm is that to compute this h of x star, okay, or rather negative h of x star and all that, and then pass it through the relay function, and then you get it u star actually, then it will implement. So, this is essentially a closed loop time optimal control implementation, much desirable compared to this structure really. Okay. So, let us see how you do that, at least in a small example sense actually, which is a very standard example in textbooks of course. So, here we are talking about time optimal control of double integral systems really. Okay. Now, these double integral systems appear naturally in many applications, and the very simplest form I can think about is just a spring mass application actually, not even no damper, just spring mass actually if you see that. Okay. So, here the vibration is something like my double dot is f actually. The same thing can be expressed, you can visualize a frictionless car moving on the road. Okay. The moment you apply a force, there is acceleration, things like that, dragless airplanes actually. So, then it will happen like this equation will observe like that, I mean this equation will be observed. Even in electrical circuit similar things can be written also basically. Alright, so the state variable we can define x1 as y and x2 as y dot, okay. Then the double integral system can be written very easily rather, that x1 dot is x2 whereas x2 dot is u is nothing but f over m. So, essentially you are writing y double dot is nothing but f by m, and then defining this first canonical form, okay, you can first companion form, you can write this way very easily. The difference here is u is constrained again between -1 and +1, that is what it is given here. Okay. So, once this is in place, I tell okay what is happening, we will see that in a much more detailed sense actually. So, we come back to this problem and tell okay system dynamics is x1 dot is x2, well x1 dot is x2, okay, whereas x2 dot is u, okay, and this is subject to this constraint that I mean magnitude of u is bound between -1 and +1, and then that constraint is valid for all time between t0 to tf. The objective is to find an admissible control history such that this condition x1 0 x2 0 is driven towards origin in minimum time. And here you are assuming a normal time optimal control sense, that means no singular control. And you can very clearly see that this controllability is actually defined. In other words, okay, controllable this is actually a state controllable problem actually. So, you can see that this can be written as x dot equal to okay ax plus bu, okay, u is 1 here of course. So, this is nothing there, and x1 dot is x2, and that is what it is actually. Okay. So, this is your A matrix and that is your B matrix. So, controllability matrix if you formulate, sometimes people write as Z, sometimes M like that. So, this is B and AB, okay. So, that is nothing but something like 0 1, and if you multiply that it still becomes 1 0, okay. This is 0 0 plus 1 times 1, this is 1, and then obviously second one is 0. So, this is if you take determinant of z, okay, and obviously the determinant is happens to be minus 1, which is not 0. So, obviously the state controllable problem actually. Okay, so normal time optimal control condition is valid here. Alright, performance index as usual we select Tf minus T naught minimum time problem actually, and Hamiltonian is also very straightforward, 1 plus lambda transpose f actually. So, lambda transpose x plus bu. So, essentially lambda 1 times x2 plus lambda 2 times u. Okay, so, we write that way, and according to this Pointer's minimum principle, this condition has to be satisfied, that is the critical observation. So, if I substitute this, okay, this expression, once with respect to u star, the other one is with respect to any other u, these two quantities will cancel out. Okay. What will remain is only this quantity, lambda 2 of lambda 2 times u star has to be less than equal to lambda 2 times u. Okay. So, the optimal control should be u star is nothing but negative signum of lambda 2. So, that is a very clear cut observation actually. So, all that we need to know is lambda 2 really. Okay. Now, how do you find out? We go back to the Costate equation now. Now, remember lambda dot is minus A transpose lambda really, but you can go back and tell okay, lambda 1 dot is nothing but del h by del minus del h by del x. So, h is here. Okay. So, del h by del x1 is nothing but 0, whereas del h by del x2 is nothing but lambda 1. This can be clearly seen here. So, lambda 1 dot is negative of del h by del x1 0, lambda 2 dot is negative of del h by del x2, which is lambda 1, this del h by del x2 is lambda 1. So, it is negative lambda 1. Now, if it is 0, lambda 1 dot is 0, then lambda 1 of lambda 1 of t is nothing but the same initial condition lambda 1 0, it does not change from that value. Now, if lambda 2 dot is negative lambda 1, that means minus lambda 1 of 0, then lambda 2 t is nothing but the integral of this equation. So, lambda 1 of 0 times t plus lambda 2 of 0. Okay. So, this results in essentially this results in 4 possibilities, because this is a straight line equation, you can see that. Okay. This is like something like y equal to mx plus c sort of thing, but this is lambda 2 is nothing but some coefficient negative of that times t plus some other coefficient. So, in time and this one in time versus lambda 2 plot, okay, if I see that, it is guaranteed to be a straight line. Now, depending on the situation, it can be like that, it can be like this, it can be just a constant, it can be like this, like that actually. Okay. So, there are 4 possibilities like that, depending on the constants, this lambda 1 naught and lambda 2 naught actually. So, all the 4 cases we need to see what is happening there. So, this is pictorially written here, either lambda 2 can be like this, in which case lambda 2 is always negative, remains negative, starts negative and remains negative, it is building in the negative direction. Then, according to our law, control is negative signum of lambda 2, so control has to be plus 1. Okay. Similarly, if lambda 2 happens to be all positive, then the control has to be minus 1 throughout actually. That is very clear. Now, what about the case like this? It starts from negative, but because the slope is positive, it goes like this. So, at some instant, it actually crosses the 0 line. Okay. That means, up to that this value is negative, hence my control is positive, and after that this value is negative, this lambda 2 value is positive and hence my control is negative. Okay. So, I start with a positive value of control and I go to negative value. And here it is exactly opposite. I start with a positive value of lambda 2 and hence my control was negative, and later my lambda 2 happens to be negative, hence my control becomes positive. Okay. So, you can see the switching very clearly here. Now, the question is how to find this h of x which are hunting out here. Okay. This is in time domain, but how do you find out as a function of state? And also you are interested in which time it will switch. Okay. The time of switching is also important actually. Alright, so for that we need to develop the state trajectories, and state trajectories, in other words, we are interested in something like a phase plane diagram sort of thing. So from state equation we have to go back now and we tell okay, x1 dot is x2, whereas x2 dot is nothing but u, and now we have u star basically. So, if you redefine this u star as something like capital U, which can be either plus 1 or minus 1 depending on the situation. So, in general we can write that okay, x2 dot is u star. So, that means x2 of t is nothing but some initial condition times this u star times t, what u star is defined as capital U. So, x2 dot x2 of t is nothing but x2 of 0 plus u times t. So, then x1 dot is x2, so that means x1 dot is nothing but this expression. So, x1 of t is nothing but x1 of 0 plus integral of this, that means x2 of 0 times t plus half u t square actually. Okay. So, this expression is coming for the x1 actually. Okay. And also, I mean, these are very compatible, like if for our very early physics and all that, x2 minus x2 of t minus x2 is nothing but the velocity, and the velocity is nothing but u times t acceleration times time elapsed actually. Okay. I mean, delta v is nothing but at, and delta x, this is difference between that is nothing but a kind of a ut plus half at square and all that what you know earlier actually. Anyway, so these are the same similar expressions actually. Okay. So, x2 of t is nothing but this, okay, and x1 t is nothing but that. So, here is a possibility of eliminating this time variable, okay, because right. So, we can do that by this expression we can solve for time, okay. This is nothing but x2 minus x2 0 divided by u, and hence we can write that x1 is nothing but now time variable can be substituted and we can write it that way. And also observe that if u is plus or minus 1, 1 by u is also plus or minus 1 actually. Okay. So, wherever 1 by u is there, you can substitute with this capital U again. Okay. So, you can write it this way now. So, this is an expression between x1 and x2, including the initial condition for x1 and x2, and that don't forget actually. Okay. The moment I know initial condition for x1 and x2, this x1 at any time and x2 at any time can be written that way basically. So, using that it is very good to expression, I mean, you can write this expression quickly, that if u is positive, u is plus 1, okay, then time happens to be this expression, okay, x2 minus x2 0 by 1. So, it is x2 minus x2 0, and x1, okay, this relationship we can just drop this u because u is plus 1 actually. Okay. So, you can, if I club these two quantities, okay, that happens to be something like C1, because this is a constant number, that is C1 plus half x2 square, and in the other case that u is minus 1, we will end up with fairly similar things with sign changes and all that. So, it happens, t happens to be like that, where x1 is nothing but these quantities actually. Okay. So, C1 and C2 are constants, okay, and depending on the situation where u is positive or negative, you will end up with these expressions. So, irrespective of what, you can see that x1 is equal to C1 plus half x2 square, or x1 is C2 minus half x2 square. If you see these relationships, these are nothing but parabolas or other family of parabolas in the phase plane actually. Okay. So, depends on the constant, which again the constants depend on the initial condition values largely. So, essentially depending on the initial condition where you are in the phase plane, and phase plane is nothing but a plot between x1 and x2 really. So, in the phase plane, depending on the initial condition, we can end up with this type of a parabola or this kind of a parabola actually. So, this is what is pictorially represented here. So, you have if u is positive, that plus 1, then these are the parabolas that will result, I mean, depending on the initial condition actually. Okay. So, with time it will start from somewhere here and it will start evolving that way. Okay. If it starts from here, it will start evolving that way actually, okay, like that. But if it starts from somewhere here, it will evolve that way. Okay, again depends on u is minus 1. If you apply control being minus 1, it will happen that way actually. Okay. Alright. So, note that these arrow marks indicate evolution of trajectories with increase of time, which is obvious actually. Alright. Now, our job is not yet done. We want to find a good solution to that actually. So, what happens here? Now, at t equal to tf, our objective is to drive x1 of Tf and x2 of Tf to equal to 0 basically. So, we have to analyze that particular case, and obviously it will not happen everywhere. The solution tells us that it writes on this particular trajectory here, okay, it has to come to 0, or if it is in this side of the story, it has to ride on this particular trajectory only basically, okay, it will come to 0. Any other thing it will miss 0 and go away actually. Okay. Alright, so this particular situation you can it depends again the initial condition sort of relationship. So, we take that relationship then put it 0 0 here and end up with some expression like this actually. Okay. So, this expression what you see here is okay. Okay, we start with this expression and then we are trying to analyze actually. Okay, so we are putting this is 0 and this is 0 and then analyzing this expression really. Okay, so this lands up with some equation like that. So, essentially it is a collection of points, okay, which defines the switching curve. Again, depending on u is plus 1, it will result something, u is minus 1, it will result the other family actually. Okay. U is plus 1, this is what will represent, this is denoted as gamma plus, and if it is u is minus 1, this will result in that sense, this particular curve is defined as gamma minus actually. Okay. Alright, so these two curves will evolve, and one is called gamma plus, the other one is gamma minus. These are on this curve, we are able to transfer any initial state to 0 actually. Okay. So, formally speaking, the locus gamma plus is defined something like this, x1 and x2 such that x1 is equal to half x2 square, and gamma minus is x1 and x2 such that x1 is minus half x2 square. This is valid in this, okay, when x2 is negative, this segment, okay, in this segment x2 is negative. So, this gamma plus is defined in this segment, especially this trajectory only, and the other case is especially the trajectory again. Alright, so we can combinedly write them as something like this. We can let me form an union of these two curves, gamma plus union gamma minus, and combinedly it can be written something like that. X1 is nothing but equal to minus half of x2 times modulus of x2. Yeah, this will represent this side and that will represent that side actually. So, this is called switching curve actually. Okay. Now, accordingly, after knowing the switching curve, we can define some phase plane regions, and accordingly we will define R plus and R minus, and R plus happens to be this all these points where this condition is satisfied, x1 is strictly less than this expression minus half of x2 times x2 modulus, and R minus is the region where this x1 is strictly greater than this same expression. In other words, if once we define this gamma, which is this curve, okay, this entire region towards the left side is nothing but R plus, and entire region towards the right side is R minus actually. Okay. This is what is written here. So, now what you are telling here, the control strategy is something like this. If the system is initially on gamma plus, okay, if somehow the initial condition happens to be on gamma plus, then simply apply equal to plus 1, you are done actually. At some point of time, you will reach the final point 0 0. If it happens to be on gamma minus, okay, then you simply apply minus 1 and at some point of time it will take you to that actually again. But if it happens to be somewhere in the R plus or R minus, what do you do? Okay. Now, this observation is very interesting here. If it happens to be in R plus, let us say, so what we will do? We have to apply plus 1 control. So, the trajectory will revolve somewhere like this, and here it will actually intersect this switching curve at some point of time. Once it intersects, you ride on the switching curve, it will take you there. Okay. And similarly, if it happens to be R minus, okay, something like this, then you first apply minus 1, okay, and it will intersect the switching curve, and once it intersects the switching curve, then you change this into controller, it will take you there actually. Okay. So, very close to what is called as sliding mode control and all that. Those of you know sliding mode and all that, something very similar happening here. Okay. Alright, so now somebody can argue, wait a second, I can actually do this way also. Why should I take why should I take this negative control and go this way and then go to 0? I can actually also start with some positive control, then apply negative control. I will intersect again this switching curve somewhere, and then I will again switch the sign and go. The thing is, it is not allowed. First of all, you can clearly see that intuitively feel that this path will take more time, okay, compared to this path. Okay. So that violates the minimum time situation, and also it violates from the theorem that we told the maximum number of switches can be at the most 2 here. Okay. Sorry, at the most 1 actually. Right, you can go back to that theorem. Okay. At the most n minus 1 time. The original system is normal and it has all eigenvalues being positive and all that, then it can switch at the most n minus 1 time. N is 2 here, so n minus 1 is 1. Okay. So that kind of situation is not allowed really. Okay. This will violate that condition also basically. Alright, so what is the final form of control law? It turns out that it is positive 1 plus 1, okay, if it happens to be in this region, okay, negative 1 if it happens to be in that region actually, okay. But to implement it, we can define this quantity, okay, that is nothing but this expression, and if z happens to be positive, then we apply minus 1, z happens to be strictly negative, we apply plus 1. And if z happens to be exactly 0 and all that, then depending on x2 is positive, we apply minus 1, and x2 is negative, it happens to be plus 1. That is on the switching curve really, and these are outside the switching curve actually really. Yeah. So essentially one can observe that if you define a quantity like this and operate a control law like that, this is essentially a nonlinear control, even though the system is linear. So we will end up with a bang control for this minimum time optimal control problem. But the elegant thing is, we actually came up with a state feedback control law also basically. Yeah. Then as a curiosity, somebody wants to compute how much time really it takes to go there to the origin and all. That expression can also be derived depending on where you are. Okay. And this expression happens to be like this actually. Some references and all you can see, or you can derive it yourself also basically. Okay, so this can also be computed, and to know how much time it takes, and you can actually implement this control in computers and then monitor the time taken and all that. It will match to that value actually. Alright, so finally you can somehow, if you want to implement this control law, it's rather very easy. All that you have to do is, this is a double integrator system plant. So this is an integral here, u is coming here. So after integration, it is x2 dot, which is u. After integration is x2. That is nothing but x1 dot. So after integration, it is x1. Now here you tap x2, okay, and then generate this half x2 times x2 modulo sort of thing, and then combine that with x1. So that will give us z. Okay, that's the expression what you are looking for. Okay, that will give us z. And flip the sign and take to the relay function, and then you get your controller. So it is completely in the state feedback form actually, which is very neat to see that. And that is how we got this h of x and all that here. Okay. The closed loop expression that you are looking for, actually closed form expression results in a very neat control structure actually. Alright, so more on that you can study many textbooks, and then different problems you can see in the literature and things like that to have more knowledge actually. So that's where we will stop this lecture, and next lecture onwards we will see some fuel optimal control and then energy optimal control if time permits, and probably state constrained problems as well actually. Alright, so let's stop here in this class. Thank you.